Good morning, all viewers. This presentation is basically all about the basic calculation of weak localization and weak antilocalization in quantum transport and how the weak antilocalization signatures in topological insulators. This presentation will be summarized in the sections, and the outlines of the sections are: what is weak localization in resistivity and magnetoresistance? Second, what is weak antilocalization in resistivity and magnetoresistance? Third, cause of arising weak localization and weak antilocalization signatures in quantum materials, classical and quantum probability of these phenomena, role of interferences, either constructive interference and destructive interference in weak localization and weak antilocalization. What is the effect of magnetic field in weak localization and antilocalization? What is the condition required for weak localization and antilocalization? Effect of phase factor on conductivity, and animation view of weak antilocalization and weak localization with interference effects. And this is the animated view of weak antilocalization signatures with increasing magnetic field. How the signatures are coming. So, there are some unique properties of topological insulator. A 3D topological insulator which shows insulating bulk but conducting states on the surface. Basically, in topological insulators, in the bulk, this shows the cyclotron orbits because there is the induced internal magnetic field in the materials, and due to electrons can circulate at a certain position, and this shows the gap in the bulk, and due to which there is no conductivity in bulk, but the surface is conducting with the spin polarized electrons, and at one time the electron can movement in one direction with spin up, and on the other state the spin is down with the opposite phase. So as the electron change there, the direction of the motion of the spin also change the direction of the spin. So this is the time-divisional symmetry which holds in these systems. Second, surface states are useful because they have significant properties like possessing high mobility spin polarized charge carriers with no losses due to backscattering. So these electrons cannot backscatter and they move in the forward direction due to which there is a very high speed electrons and shows very high conductivity. Robust against non-magnetic perturbations like small doping amount of non-magnetic impurities. They will not affect a very small doping of the magnetic impurities, but at a certain value of the magnetic impurities increment, the bulk is showing the gap because the magnetic impurities perturb the topological insulators, and due to which at the surface state this shows the gap, and due to creation of the gap the time-universal symmetry breaks, and due to the breaking of the time-universal symmetry this shows the gap, and this is no longer topological insulators. For to make topological insulator, this is the condition that this holds the time-universal symmetry. 4. As these surface states are protected by time-divisional symmetry, hence these states possess spin momentum locking. Electrons with only a definite spin, either up or down, can move along a particular direction. In a particular direction, electron can move in one direction, and if the electrons change the direction, also it is required to change their movement of the electron. So this holds the spin-orbit coupling in these materials. What is weak localization in resistivity and magnetoresistance? So rapidly changing in magnetoresistance data with magnetic field in a very low domain, very low range of magnetic field. Typically it is basically observed around minus 0.5 to 0.5 Tesla typically, and in weak localization signatures, this shows the negative magnetoresistance. The resistance decreases with the increment of the magnetic field. This is basically shows at very low value of the magnetic field, approach 0 Tesla. This shows very high value of the resistance and decreases with the increment of the magnetic field. So this shows the negative magnetoresistance. But in weak antilocalization signature, this shows the positive magnetoresistance effect due to high spin orbit coupling in these materials. And at zero value of the magnetic field, this shows very low value of the resistance and increase with the increment of the magnetic field. So this shows very high conductivity at zero value of the magnetic field. And these are follow the quantum interference effects in electronic transport certain materials, particularly in systems with spin-orbit coupling. What is the cause of arising weak localization and weak antilocalization signatures? Both weak localization and weak antilocalizations are quantum interference effects that arise due to coherent backscattering of electrons in disordered materials. They hold the tensile symmetry with spin-orbit coupling. In weak localization signatures, the coherent backscattering and they do construct interferentially with weak disorder, and electron can undergo multiple elastic events so the weak localization signatures. But weak anti-localization signatures are only possible with the spin-orbit coupling materials with robust, and it is required for these materials to be the atomic numbers and the value of Z should be very high, and in high Z values the weak anti-localization signatures are and weak localized signatures are possible because they reduces the backscattering. Classical and quantum probability of these phenomena. These phenomena basically are purely the quantum effects. On the basis of the classical mechanics, we cannot explain these phenomena because electron motion in disordered medium follows the diffusive transport and they not return back to its original position. So this the random walk effect, and on the random statics we cannot explain the signatures of the weak localization and weak anti-localization signatures because there are no interference effects in classical transport. And on the basis of the quantum mechanics, we can explain the weak localization and weak antilocalization signatures because the electron transport is basically the wave-like effect, and this shows the interference either constructively or destructively interference. Weak localization. When electron takes a closed loop path, its time reversal counterpart follows the same path in the opposite direction. Due to tangential symmetry, their wave function interferes constructively, increasing the probability of backscattering, and return the probability is hence to higher resistivity at low temperatures, and with the increment of the field the resistivity decreases, and this states the negative magnetoresistance effect. But in case of the weak anti-localization signatures, the materials with very high robust spin-orbit coupling and maintain a phase of the pi phase shift between the electrons and tangential loops and destructive interference, they reduce the backscattering and lowers the resistivity and found to be very high conductivity at zero magnetic field. The important condition for the weak anti-localization signatures. So this it states that the particle size should be greater than that of the coherence length for to follow the condition of the weak anti-localization signatures. And the second one, the coherence length should be greater than that of the mean free path because to maintain the phase. So this states that coherence length should be greater than that of the mean free path. Electrons will maintain their phase coherence even after being scattered for many times. And second one is that quantum interference between tangential scattering loop will be possible, and then only the interference terms will change and result in a change to the conductivity. For to the weak localization signatures, the conductivity should be negative with very spin orbit coupling, weak spin orbit coupling, and for the robust spin orbit coupling, positive weak anti-localization signatures, conductivity positive. And on the basis of the classical mechanics, this states that the time reversal symmetry holds the up spin and down spin counterpart, the eigenstate should be same. So the counterclockwise and anti-counterclockwise electron, the corresponding probability, it should be stated that this is approximately the same. So on the basis of the classical mechanics, we cannot explain these features of the weak localization and weak anti-localization signatures. So what is the effect of the magnetic field on weak localization and weak anti-localization signatures? What is the condition effect of phase factor on conductivity? So on the basis of the quantum mechanics, we can explain the signatures of weak localization and weak anti-localization. So the wave function of the clockwise electron with the corresponding static wave function and phase factor, and wave function of the counterclockwise electron corresponding steady wave function and phase factor, and the total wave function after the interference effects. This is the total wave function, and if the electron do construct interferentially with the same spins in the same direction, so this is the probability of the electrons. And if the electrons do construct destructively interference with the opposite phase, and the corresponding probability in the case of the weak antilocalization signature, it should be 0. On the addition of the magnetic field, so the phase factor increase and the corresponding wave function is this, so the probability is increasing with the magnetic field. And this is the one of the example which is SNT, which is basically a topological crystalline insulator. This state that the conductivity decreases with the increment of the magnetic field in a very low domain of the magnetic field. So this state that the weak antilocalization signatures are coming in a very low domain of the magnetic field. The explanation on the basis of the quantum mechanics. So when the electrons do constructive interference, the probability should be, in the case of the weak localization signatures, is very high. So the electron can residing at a certain position is very high, and this reduces the conductivity. And in case of the weak antilocalization signatures, when the electrons do destructively interference, and in that case, on the case destructive interference case, the probability exerting at a certain finding of electron at a certain position is very less, and it is approached due to, so the electron can move here and there very rapidly. So the conductivity is increasing, and with the introduction of the magnetic field, this decreases. So with the addition of the magnetic field and on the surface states, the conductivity enhanced and it decreases with the magnetic field, because electron can move and here and there, because they are at a certain position the finding of the probability of the electron is very less. But the addition of the magnetic field introduce an extra phase factor which increases the probability, and this is the total wave function of the electrons. And on the application of the magnetic field perturbs the direction of the spins and also influences the spin direction, and this increases basically the probability of the electrons of finding at a certain position, and it can reside at up to a long time, so due to which the resistance increase with the magnetic field. And this is basically not existing to maintain a phase coherence of pi. So important signatures of 2D weak antilocalization signatures in the case of the parallel magnetic field and perpendicular magnetic field. In the case of the parallel magnetic field not change the direction of the electrons. So that's why this shows the purely basically the classical type of the behavior and shows the parabolic behavior. But in case of the perpendicular magnetic field aligns the spin in their direction, and due to which the spins effect, and this was the weak antilocalization signatures. This is the animation view of the weak localization signatures, in which the electrons have been shown here with the symmetric diagrams, and the electrons are in the same spin, and also the electrons are in the same spin. And these are the eigenstates, which states as yellow and blue. Electron can reside in the state at a same time, because the Pauli exclusion principle, at a time electron can reside in one state but the energy is same, and with the same spins, and they do construct interference. And in the case of the construct interference, this shows with the increasing of the magnetic field, the weak localization signatures increases, the conductivity increases with the increment of the magnetic field. And this is the animation view of the weak antilocalization signatures when the electrons are in the opposite phases with the opposite momentum, and phase factor is basically is equal to pi 180 degree, and electrons in the spins with opposite spins are moving on the states with the surface states in the opposite direction, and they do constructive interference, and electron can either reside in the yellow state and blue state, but at a certain time they can reside at only a certain state because they follow the Pauli exclusion principle, and with the increment of the magnetic field, this shows the weak antilocalization signature. The conductivity decreasing with the increment of the magnetic field. Thank you very much for your kind attention.